Today we are going to talk about the advanced encryption standard, and we are going to use the finite field arithmetic. The finite field arithmetic means that we will not get out of the field. We will make a multiplication modulo GF of 2 to the power 8. And we know that the field is going to be finite field only if it has a multiplicative inverse. This is theoretical part, you can read it. But here, this is the most important part. We have two operations, the addition and multiplication. The addition is done simply by XOR operation, and the multiplication is done by using the modulus to the irreducible polynomial. We are going to use this irreducible polynomial here, x to the power 8, x to the power 4, x to the power 3, and x and 1. This irreducible polynomial will make sure the field is not going to, the multiplication or the result of multiplication will not get out of the field. We will always stay in the field. For example, if we have two numbers and the most significant bit is 0, this is going to be translated as a simple XOR operation. But if the most significant bit is 1, this means that we are going to have carry in the operation. Then we have to use the mod m of x, which is this one that we are going to use here in the finite field arithmetic. Here we started to see the AES encryption. Here we have the input, and we have input to state matrix. This input to state matrix is going to be like a place to save the result of each round. And then we have the initial transformation, and then this is going to be done only once. And then we have rounds and another round till the number of rounds that we need. And then the final ciphertext is going to be put here in the state matrix. We have also the key expansion, means that we have a key with some specific number of bits. This key is going to be expanded to a number of subkeys. Okay? And this is the general structure of the AES encryption. We're going to get into the details of each stage here until we understand each round, and we get into each round and we understand the internal structure of each one. So for example, this is the general structure. Here we have the state matrix. We define it like if we have input data, the input data is arranged in column wise. For example, this is 0, 1, 2, 3, 4, 5 column wise. And also here, this is going to be column wise, and until we get the output here. Why it is column wise? Because we are going to use the keys the same way, but we will take this word, we apply the same operation together with the corresponding input text from the column here. We will take one column here together with one word in the key. One column here together with one word in the key, and so on, until we get to the last one. Here we have different types of AES. Actually, we will take the first one, which is 4 words, 16 bytes, and 128 bits. And you can see we have different types of AES, but for simplicity, we will study the first one only, which contains the four words. These 4 words is the input, or 128 bits is going to be input for the AES algorithm. And we have 10 number of rounds are 10, and also round the key size 4, 16, 128, and the expanded key size is 44. So we will create 44 subkeys. Okay. Here we get into the detail of the internal structure of the rounds. The add round key, the first transformation is to add a round key. So for example, each round has the corresponding round key. We get the sub key from here and then add a round key together with the plain text. Then we get into each round. Each round has four main operations. The first one is called substitute bytes. The second one, or the second operation, is shift rows. The third operation is mix columns. The fourth operation is add round key. These are the internal structure of the rounds. It contains these four operations, and we will get the detail of these rounds soon. So we have round here, round one, we have round two, we have round 10. As we said, we will concentrate only on that first type with 10 rounds. And each expanded key, after each round, we have to make the add round key. Each After each round, we will do only one at the beginning, and then in each round, the last stage will be add round the key, add round the key, add round the key. So we can say about the structure is not feastal structure. Anybody knows what is the feastal structure? Anybody can share me what is the feastal structure? This is not feastal structure. What does this mean? Anybody knows? Anybody here? Do you?
No, doctor, to be honest.
We studied feastal structure in the previous lecture. Do you remember the feastal structure?
We, I do remember we took it, but I forgot,
Yeah, okay.
to be honest.
Oh, no problem. Okay. So the feastal structure is just, if you remember, the feastal structure is just, okay, let me draw something for you. The feastal structure is like the data is here and it is divided to left and right, left and right. And the feastal structure saying that we swap. The right hand side goes to the left hand side and the left hand side goes to the right hand side, but after the key operation here, XOR, okay, this is operation F function, and then go to XOR with the left hand side. And then the result will be put in the right hand side. So we have, this is the feastal structure. Actually, it is to have a swap of, we have dividing the input data to right hand side and left hand side, and we swap each of them. Simply we swap. Forget about the key expansion and the XOR. Just simply remember that we swap the parts. But here we don't swap anything, so this is not a feastal structure. That's why he said this is not a feastal structure, because we don't divide the input to two parts and we shift the right hand to the left and left hand to the right. So here it is not really a feastal structure. And for the key here, we have a key of 16 bytes. These 16 bytes are extended to 44, 44 32 bits words. So one key of 16 bytes is extended to 44 keys. it is extended to 44 keys. And the structure is quite simple. It is like, as we said before, we have rounds, round one, round two, they are similar. And also for the inverse, the inverse way around is it has the same round internal structure. But actually here, the encryption and decryption, they are not identical. We have to implement them separately. They are not fiscal structure. This is the second property of fiscal structure. If we remember, fiscal structure is decryption is the inverse of encryption. But here, decryption is not the inverse of encryption. It is different, little different. Maybe is little similar, too similar, but not identical. Too similar, but not identical. So here we define the structure is not a feast, as I told you, this is not a fiscal structure, means that the data is not divided to right and left and then swap, but it is just one block is passed to the other rounds without any of this permutation, the fiscal permutation. And also the second property is that the encryption and decryption are not identical. But in the fiscal structure, they are identical. We can get the same output in the encryption and the decryption. It is the opposite direction, but they are identical. You can use the same algorithm to do both operations. Simply, if you look at the structure of each round, we take one round here, this one round, and then zoom out this round. We zoom it out to see it like that. This is the internal structure of each round. So the initial state here is passed to the sub-bytes operations. The sub-bytes operation is simply substitution with the S box. I will tell you about the S box right now. And after that, the result is moved to the state array again. And the state array transfer the data to the shift rows. Shift rows is simply simple shift rows, simple shift. So moving the bytes from right to left or from left to right. This is simple. And then the result will be moved to the state matrix, and then after that it moves to the mix columns operation, and then moving to the state matrix again, and then last we add a round key, and then the result of the round is saved into the state matrix. So we have mainly here, we have the sub-bytes. This is the first operation. We have shift rows, which is the second operation. We have mix column, the third operation. And finally, we have the add round key, which is the fourth operation or last one. These are the operations into each round. Inside each round, we have these operations actually. Okay, just give me a second. Okay. Okay, so here again, we say this again because this is the main building block of the AES encryption or the AES algorithm. The first operation is the sub-bytes, and sub-bytes contains the S box replacement or substitution, and then shift rows, This is simple shift from right to left or from left to right. And mixed columns, I will tell you about the operation of mixed column. It's just multiplication operation in the GF of 2 to the power 8. And the add round keys just XOR each key with the result. And that's the internal structure of each round. And here, the detailed structure. Please pay attention to this slide because it contains the internal detail of each round. Or you can say the detailed structure is talking about the algorithm detailed structure. It is, you can say, this slide is very important because it explains the algorithm in detail. So here we process the entire data block as a single matrix during each round using substitutions and permutation. We are not dealing the block as a feasted cipher, as I told you, is not divided to two parts, but it is an entire data block. We are dealing with entire data block. The second property is the key that is provided as input is expanded to array of 44 32-bit words. So the key is just a simple key is going to be expanded to 44 32-bit words. And these are the internal operations inside each round. The sub-bytes, we are going to use an S box to perform a byte by byte substitution of the block. So we are going to replace, is a replacement of bytes. We have sub bytes, or we have S box, and then we are going to use that S box to replace some bytes. For example, I take A and then replace it by C. Simply like that, substitution. And the shift rows is a simple permutation. Shifting right to left or left to right is just simple permutation. And the mixed columns, this is a substitution that make use of arithmetic over GF of 2 to the power 8. We are going to use the arithmetic here of GF of 2 to the power 8 in the mixed columns. And for the add round key, this is simple bit-wise XOR of the current block with a portion of the expanded key. We have expanded key, we have part of the data, we are going to use XOR operation to have a result of this operation, add round key. We apply add round key, the last stage in each round. The cipher begins and ends with add round key stage. We have to understand this. This is, if we return back, let me return back to remove this drawing and then return it back. This one. So it starts by add round key, is not here actually. Here, it starts by add round key and ends with add round key. Starts with add round key and ends with add round key. And take care, you see each round is 4 stages, but the last stage is only 3 stages. The last round is only 3 stages. Substitute bytes, shift rows, there is no mixed columns, the add round key. And the opposite way around in the decryption. So all the rounds are 4 operations, but the last one is 3 operations only. There is no mixed columns. So the cipher begins and ends with an add round key stage. We can view the cipher as alternating operations of XOR operations and scrambling of the block, the other 3 stages, followed by XOR encryption and so on. It's like we have, we are changing the XOR operation. We have add round key. This is an XOR operation, and followed by scrambling the block, the shift left and shift right. This is a scrambling of the block. Scrambling means changing the order of the data, and followed by XOR operation, and so on. This is just in each round happening like that. We make XOR, then we scramble, XOR scramble, XOR scramble, until we get totally different data compared to the initial input. For example, the initial input is Osama. I get totally different letters, totally different. This is encryption, totally different data. That's why we do all of these operations. We need to make different output. There is no relationship between the input and the output, and also the diffusion. As I told you, if I change single bit in the input, this is going to change the entire output. We are doing all these operations to make sure of diffusion and confusion. Diffusion means if we change single bit in the input, this is going to change the entire output. And the confusion means we cut the relationship between the input and the output. That's why we make all these complex operations. We need to make sure that the output is totally different compared to the input. So each stage is easily reversible. Each stage, take care, is not the entire algorithm. The decryption algorithm makes use of expanded key in reverse order. However, the decryption algorithm is not identical to the encryption algorithm. They are not identical. State is the same for both encryption and decryption. This is the state means the store, number of stores here, that square is similar here for the encryption and decryption. The squares here, these are the state matrix, and also the state matrix here also is appearing here. This is the state matrix. He's saying that they are the same in the input in the encryption and decryption. The final round of both encryption and decryption consists of only 3 stages. And that's apparent, as I told you, we have the last round with only 3 stages. Okay, this is the detailed structure of the, let's move to the operations in detail, each one in detail. The first one is sub-bytes. Here we have the input. This is the input matrix. As I told you, we arrange it in column wise, and then we take each byte here, and then go to S box, and then we index it row by column, and then extract the corresponding data and replace it to the corresponding byte. So let's take an example. For example, if the input data is EA, what should I do? I go to the S box, EA, take care. Concentrate with me. I'm going to ask you about this. EA. I want to make sure that you understand this operation, because this operation is important. So EA here, I go to the S box. I see EA. So this is E, and this is A. The intersection of EA is what? 87. So I return back. I cannot return easily here. And the corresponding is the EA is we get out 87. I remove EA and put 87 instead. So if EA is here, I go to the S box and then extract the corresponding data and put it in the corresponding byte. Okay, what about 04? Anybody can help me? What is the output of 04?
Doctor,
04
Yes,
Zero nine.
F2.
F2.
04 is F2, yes. 02 is F2 from here. This is the first row, which is 0, and then the fifth column, which is, so the intersection together,
Before 4, Doctor, not 5.
04, yeah, okay. So yeah, because it started by 0, this is confusing. So 04 is F2, so here we put F2. And 65 we will get 4D, and so on. Okay, you understand the operation? This is just a simple substitution. It's called the sub bytes. This is not, this is more, this is the most, or the easiest one of them. This is the easiest one of them. You get a byte and then go to the S box and then extract the corresponding byte and put it instead. That's simply the sub bytes. What about the second operation? We have also, I don't want to forget this. We have also S box for encryption and the inverse S box for decryption. So they are totally different. One for the encryption and one for the decryption. And this is done to make sure that we can extract the data back. We are doing the inverse, and as I told you in the mathematical part of the lectures, I told you the operation must be traversed. I mean, we can go forward and then we can go back. So here, all the calculations are done to make sure that we can extract the data back from the encrypted data. So S box here and the corresponding inverse S box, and this S box is used to calculate the inverse S box. This is not random numbers. This is not, maybe S box is randomly created, but the inverse S box is calculated. The inverse S box is calculated. How it is calculated? This is the way it is calculated. So we have here the XY. This is the input. And the inverse of the XY itself. How to get the inverse of the XY? This is simply done by the multiplicative inverse. This is another table. This is different table. This is not S box or inverse S box. This is the inverse of all the permutations of bytes in the GF of 2 to the power 8. How can we calculate the inverse of each byte? We have a byte here. This is just a byte, you know, the 8 bits. 8 bits is coming to this one. And we calculate all the inverses of these bytes. For example, 00 has inverse of 0, 01 has inverse of 01, and 02 has inverse of 8D. How did we calculate this? Do you know how to calculate?
No,
How to calculate this?
Doctor,
Yes.
I think inverse is seeing the binary then -1 or +1, I think.
I don't know. I told you about that. I know the name of the algorithm. Do you know the name of the algorithm?
No, doctor, to be honest.
Yes. This is not simple operation. This is not simple. This is not multiplication or XOR or something. This is very complex operation. And I told you in the lecture, don't get the detail of the algorithm. I want you to know the name of the algorithm only. Do you know do you remember this name? The name of the algorithm that we use to calculate the multiplicative inverse. I told you we cannot calculate the multiplicative inverse by hand or by simple way. I can improve that the multiplicative inverse is true. So I do some operations to make sure that it gets a remainder. It gets a remainder of one. I get a remainder of one is okay, because uh, this is irreducible operation, and it gets a remainder of one means that we multiply two bytes, one and its inverse together to get one. The result is one. So we have the result is one means that it's correct. I can prove that it's correct, but I cannot get the inverse itself. The name of the algorithm is the Euclidean algorithm. Euclidean algorithm. Okay, I cannot do that manually. I have to make computer program to make it. So the calculation is not simple. We have to use the Euclidean algorithm to calculate this table, and then get this one byte to bit column vector, and then use this matrix multiplication together with the bytes that I get from here. And then after that, I extract this and get it in the S of YX. For example, the YX is, for example, AB. And I want to implement the S box. So I go to, this is the S box that I want to implement. This is not the S box, this is inverse. This is just an inverse table. This is not related to S box, so don't be confused. I have S box here. Okay, and I have, for example, AB. For example, AB is little down here. This is A, and this is B. I want to know the value that I should put it here. I want to know. So I get AB and then move to AB here. This is AB. This is 4A. I take 4A and convert it to binary representation and make this operation multiplication, and then get the output, and then put the output into the corresponding S of YX. So I get the output, for example, anything, I don't know, for example, 3B. So I get 3B and put it here. And then get another byte, and then calculate it, then put it in the corresponding cell, and so on. That's how we calculate, or how to implement the S box. Let's get a numerical example. For example, the 9-5. This is 1 byte that we want to convert. The first thing is to go to the 9-5, and 9-5 is here, right? Is 8A. So the output is 8A. This is the output, 8A. And then we represent it by binary, and then put it here in reverse order. 0, 1, 0, 1, 0, 3 zeros, 3,
Dr.
3, and
8A
1.
hexa?
Yeah, everything here for simplicity, it is done by hexadecimal representation.
Doctor, can you repeat it again?
Okay. Here I told you about the S box. Why we need to implement the S box. We have to, this is not random numbers. I told you this is not random number. Why? Because we want to make sure that we can extract the data back from the encrypted data. For example, the input data is, for example, Ahmed, and the output is numbers or symbols. I cannot understand numbers or symbols. And the inverse operation is taking these symbols and numbers and then get Ahmed back, get the word Ahmed back. So the operation should be done mathematically, traverse it. I can inverse the operation. How to do that? It just by making these calculations. So S box is calculated and the inverse S box is also calculated. These are not random numbers. How this is done for the S box, we do the operations like this. If you wanted to have, if you want to understand more detail about this, you can refer to the textbook. You can refer to even the textbook, he referred to references on how this, why we use this structure. But anyway, I don't want you to get into the detail. I just want you to understand how this operation is done. So I have here, for example, I have the input is 95. I want to convert 95 and put the corresponding value in the S box. How to do that? I get 95, I go to the inverse matrix and then extract 9 and 5. 9, 5 is 8A. So I take 8A and represent it in binary. Here, the representation of 8A in binary. This is 8, which is 1, 0, 0, 0. This is 8. And this is A. And A is 10. The corresponding value is 10. So 1, 0, 1, 0. I reverse the order of these bits and put them here. So the first letter is not, the first number is not the right number, is not the left number as usual, but it is the right bit. For example, this 0 is here, 1, 0, 1, 3 zeros and 1. Okay, and then I do the multiplication normally, like XOR. This is an XOR operation. And then do that XOR with the row here, the column here. And then the result is going to be 0, 1, 0, 1, 0, 1, 0, 0. And 0, 1, 0, 1, 0, 1, 0, 0 is represented as 2A. Is represented as 2A.
دكتور أول جدول اللي على اليسار هذا جاهز؟
Yes, this matrix.
Yes, doctor.
Yeah, it is ready. You don't know. You don't need to know why is that done like this. You don't need to know the proof of how of this matrix. I just want you to know about it, and then if I ask you any question related to this, I will put this matrix to see it.
Because we thought, doctor, we have to learn how to find it out, but now it's a constant thing. It's just fine.
Yeah, it's like that one. I will not ask you to tell me how you get 8D from 0 to. This is impossible. It's not a question. You understand the operation is okay. I want you to understand. If I ask you how to get the inverse, the multiplicative inverse, you tell me we use the Euclidean algorithm. I don't want you to tell me the Euclidean algorithm. Maybe in a lab or something we can learn how to make the Euclidean algorithm, but for now I want you to understand the general concepts, because if you get into each one of each box is like black box. You get into the black box, you find another black box. You get into the other black box and so on. This is infinite loop. So it's better to understand the general structure. You can say we get to 1 or 2 levels only. We don't go deeply into the algorithm. And that's okay for you. You want to understand this as a bachelor degree. If you want to get deep, you can get a master degree or something. But for now, you understand the general structure of the operations. And for this operation is easy, even this one should be done like that. 0, 0, 1, 0. 0, 0, 1, 0 is 2. So it is 2 here. And 1, 0, 1, 0 is the similar to 1, 0, 1, 0 here as the one here, 1, 0, 1, 0, this one. So it is A, okay?
I want to ask from where we get that the third and fourth and fifth column.
this also the equation. I want you to know only this one, how to put this one, and how to get the output. And the other one is just here. We multiply, for example, we multiply this one by that one. This is multiplication. And also you have to know this multiplication is not simple because this contains, I will tell you about one operation, just one operation to tell you how to make it, maybe in the next session after the break. The multiplication, you have a carry here because we have in the bit 7 is 1. This is going to give us a carry. This one, we have to use the GF of 2 to the power 8, and we are going to use the irreducible polynomial. It is a polynomial multiplication. It's not a direct multiplication. But if the last bit here is 0, we can use XOR operation directly. And that's why we cannot say it is just a simple XOR. We have to look at the last bit here. If it is 1, we have to make the multiplication in GF of 2 to the power 8. If it is 0, we can make it simply XOR. And I will tell you about one of these operations after the break, okay, in detail. So I multiply that by this, and then I get this number here, 1. I multiply that by this, and then get, this is matrix operation. If you study, how to say, linear algebra, you know linear algebra? Did you study the matrices? Anybody study the matrices and know how to make matrix multiplication? Nobody? No. I see your plan. Your plan has the linear algebra.
We did linear algebra and we know about the matrices, but we need to know only how we did this. Yani we used to do like normal numbers, normal matrices, you know.
I know, yes, but this is this is different because we are using XOR operations, right?
Yes.
Okay. Okay, so let me, I will tell you about the multiplication and how to make the multiplication. I told you about that in the after break. Of course, I remind you by the operations if you know how to make a polynomial, how to make this a polynomial. This is 1, this is x squared, this is x cubed, and this is x to the power 8. And then this polynomial is multiplied by that polynomial, just a simple, like the multiplication that we learned before in the finite fields. And then we make the longhand division, by the irreducible polynomial. And this operation, I will tell you about one operation and you will understand what I'm saying. For now, I want you to know that I multiply that row by that column and the result is 1. I multiply that 1 by that 1 and the result is 0. I apply that 1 and so on. And then we take these two operations, two columns, and then make XOR, and then I get this result. Okay, and this one also, I don't want you to tell me how we get it. This is just theoretical part of the algorithm. This part and that part. If I give you an example or a test in the test question in the test, I will give you these two matrices. Okay. Okay, I think we have We don't have too much slides today, so maybe we can think about a break. Okay. Okay, so we take a break for 30 minutes. Okay, we take a break for 30 minutes, and we return back. I think it will be at your time 1 o'clock. Is okay for you?
Yes, doctor.
Okay. Okay. So just to give me a second to take the attendance.